Good morning, humans and robots alike. Now we will be talking about different types of doing Bayesian estimation. EKF, namely in this lecture, we'll be looking at EKF and how that works in the setting of SLAM, as well as we're looking at EIF and first looking at the limitations of EKF and then my EIF, and then further looking at in just a little bit initially about what different methods for Gaussian estimation exist. So just a recap of Gaussian estimation. We had a prediction step, a correction step. Prediction step allows you to take the internal updation of, okay, what was your input signal, how is usually your states evolving into consideration, and then predicting what your next state would be. Correction step was looking at the surrounding, figuring out where you are, and then updating that as well. So Bayesian estimation really had two steps, prediction and correction step. And now we'll be looking at what we further can do with it and how we can actually use this in SLAM setting, right? So there are two methods. One is Gaussian filter. This is where EKF SLAM will come into play. Then a particle filter and graph-based SLAM. Particle filter is usually used nowadays for localization in the modern SLAM methods, and we'll not talk about it much anyways, but I'll be giving you a bit of a understanding into how that works in today's lecture towards the end. Then you have graph-based SLAM, where you use optimization techniques to do the SLAM estimation. This we'll be looking at in the next lecture. Gaussian estimation, here we assume that the noise or whatever in your motion or observation model is Gaussian in nature. The motion or the actual observation given a particular state might be linear. Why I say might be linear is because you have this thing called as linearizable. So I should rephrase it as that the motion and the observation model should be linearizable in nature. Right? So let's start looking at things. Before we look at what the Kalman filter is and things around it, uh, let's first understand the state space equations of our system. So this is our xt. In this, xt is the current state of my body, ego, and xt minus 1 is the current state of my ego. And then I'm predicting the next step, which is xt. And this is what we are trying to predict, right? So this is the prediction part. Now, given my control input ut and this xt minus 1 and some noise epsilon t, we'll be looking at how it does start. Now, obviously, the previous step, I'll give you a bit of an intuition why this works, but AT tells you how the state evolves over a period of time. BT tells you how a control input gets converted into a state update. Let's look at this in a more of an example fashion. Now think you have a barrel rolling down a hill. In this barrel, you even if you don't in the scenario of this barrel, even if you don't push it or pull it, the barrel will still update its position. Why? Because it's rolling down and gravity exists, and gravity is not part of the control input which you give to our system, right? So in this case, there is this AT which allows it to understand, okay, how this state evolution happens, and that's what we mean by AT here. Now imagine you have the barrel being pushed down or pulled up either ways, and because of that your state evolution might be a bit slow or a bit faster compared to which direction this force is acting on or this control input is acting on, right? And this control input conversion to this new state is done using the help of BT. So I think that's fair now. So we have noise, let's go. So next thing which you have to look at is observation. Now the problem with observation is you just can't like mean given a particular state, you will see a particular observation. If I am in aerospace department at ISC, I'll see a different picture. If I am at EC department at ISC, I'll see a different picture. So different state in turn results into a different observation. And this is what that equation tells. So given a particular state, what is the observation which is going to look like or the measurement going to look like? And then you add noise to it because friendly neighborhood Kalman filter always wants noise, right? So we need to add noise here. Now, this is just a reminder again that our system, we are considering things in a probabilistic fashion. There are two things required in this probabilistic estimation. One being our mean the other being our standard deviation, sigma t and nu t, or nu naught or sigma naught, right? We need to use this in Calvin. So how do we do that, right? Let's look at that. So considering state evolution, we will first update our mean. Mean is what? Previous, I mean, how the state evolves, add to that my control input. So I put the BT matrix there, and that's how my new mean comes out, right? So previous mean I take in consideration, and then new mean comes out. Covariance is where things get little bit interesting, right? So previous covariance gets multiplied with I mean, how my evolution happens over a period of time. Add to that, I will add a constant noise into my system. And that's important because that plays a lot of roles down the line. Now, covariance again, I can't obviously add it in my mean. So I usually add it in covariance so that it expands the covariance or retracts. I mean, usually it will not retract, but it expands the covariance the more noise there is in my control. And if there is a shaped noise, then you will see a shaped noise. And the AT is more like, oh, because I'm here and I have not done anything, but am I sure I have not done anything? So it will like keep expanding the covariance. So imagine a 2D covariance, it'll just keep expanding this. We'll see this more in towards the end where we are implementing in SLAM. You'll see these two variables play play different kinds of roles, right? Now, we finished our prediction step. Now, skipping to correction step. Correction step needs to take two things into consideration. My measurement covariance, so noise in my observation, as well as what my measurement is, which is ZT. Now, just to give a bit of intuition behind, is this correct or not? What small experiment which you can play is, imagine QT is 0, so you have no noise in observation. It's almost perfect. If that is the case, this whole term gets divided by this whole term. You will cancel out the things, and then when you put KT here, or let's say even if you put KT here, it's I minus CT, so sigma T. So that's just becomes again 0, right? Because your CT will cancel out each other. And that's interesting. So that basically means my covariance in my position estimate will become 0 if my noise in observation is 0. So I hope that gives a bit of an intuition as to how things are moving around here, right? All right. Now, you could have asked me, Saksham, why did we assume linear function? Because a lot of times my motion models and my observation models are not linear in nature, right? So if we go to our initial slide of state equations, you see it's a linear in nature. It sometimes might not be that case. So what do we do then, right? But before we think about that, let's think about why it matters in our way of doing things. So in our way of doing things, we our input is a Gaussian noise. UT, sigma t, both are Gaussian. I mean, this whole thing is Gaussian in nature, and that's why we are doing it this way. Output is again Gaussian. So yeah, this is an important point here, right? Now, imagine when we pass a Gaussian distribution into a linear equation, the output is obviously another Gaussian distribution. Why? Because your ax plus b can only shift and increase or decrease the covariance, right? So that's what you see. We shift the x is shifted in the y-axis. It's not no longer at 0.5. It's at around 3.5, and the covariance has decreased. It's gotten narrower in just terms of looks, right? Great. So let's move forward. Now, what happens if I pass the Gaussian distribution to a nonlinear function? So the blue signal here is a gx function, is a nonlinear function in nature. Just to give a bit of an understanding of how a Kalman filter could work on it, let's think that there is a line passing through this Gaussian, I mean, passing through this nonlinear function where the MSE score is minimized for all the points which exist in the gx function. So we get that linearized GNU line. Given that, given that I given that I input a Gaussian distribution into it, I get this yellow curve as an output. Now, to get the true Gaussian distribution, what I have done is I have taken this nonlinear equation, sampled all the numbers of my Gaussian distribution here, gotten an output, and then plotted that output as well, just for our understanding. Because I wanted to show that this is not Gaussian in nature. Now there are two problems. If we do this yellow line way, you can see that the true mean and the Kalman filter mean aren't really coinciding, and the difference is quite a lot, right? It just looks too much. Another now problem is if we don't do this approximation, we do we just multiply it and we are fine with any output which comes out. That's again a problem. Why? Because the curve is not Gaussian anymore. Distribution curve is not Gaussian anymore. And because it's not Gaussian, you can't reiterate that step of Kalman filter for the next iteration because we did it only for Gaussian distribution. So what do? We still want the mean to be at least close, right? So we do this Taylor approximation. This is where EKF comes into play. In EKF, so first what you do is in your Gaussian input Gaussian distribution curve, you find the mean. At that mean point in your nonlinear curve, you take a first order Taylor approximation, which is just a tangent to that curve. That curve acts as your linear approximation. You multiply this Gaussian to that linear approximation, find a distribution curve as an output. That distribution curve's mean is a lot closer to the true mean. Great. What could be better is if we can do some sort of sampling, and that's where particle filter comes into play. What you do here is in your nonlinear curve, you sample some random points, maybe 100, right? Multiply the Gaussian curve, get an output. Now, this is not how particle filter based approach definitely works, but I'm just to showcase apples to apples. What I'm doing now is out of the sample data, which output data we got, we are now taking a Gaussian distribution curve of it. When you do that, the mean is a lot closer to my true mean. And that's a very important distinction. But problem with the particle filter based approach is it's just too heavy to compute. And that doesn't really help when you have to run things in real time. So coming back to EKF, what did we do? We had taken differentiation. So if we differentiated, we took a linear approximation, right? So this GT term are basically my differentiated terms, the Jacobians of my matrices, and that's how they are also now in capital and stuff. All right, so let's move on to implementing EK-based estimation in real time and like see how things could actually work. Before we do that, I'm defining two state variables. XT, I mean, XT is not really the variables I'm looking for, but that's basically the actual location in my, let's say, the back end of my simulator or the real world life, right? That is my, so X, Y are my real locations in the 2D space. Theta is my heading. M1 X, M1 Y is my X and Y coordinate of first landmark. M2X, M2Y, second, third, fourth, fifth. So N landmarks is what we have. Because it's 2D, so X and Y, X and Y, X and Y pair. But XT is not how we would see the world. How we would see the world is in terms of mean and covariance. So in mean, we have this new T term. Covariance, we have this whole joint joint covariance term, which is big matrix which you see, right? So nu T and the sigma T terms are the terms which you're going to play with in today's walkthrough. So before we do that, we know that if I have to first I have to take the prediction step, right? To take my prediction step, I need to only update my robot's position, not my landmark's position. So to do that, I'm going to use this fx term. What this fx term does is it will make sure that motion only impacts the robot, not the landmarks. And because each landmark consists of 2D, x and y position, we have a 2n 2n appended zeros into a matrix. All good so far? Now, we are using this fx matrix to convert this 3D state of ours to a 2n plus 3D state. The third is not my z, but rather a heading. So x, y, and heading is how that 3D part is coming into play. Motion model is what you see here, right? where I have delta x, delta y, given my linear velocity, angular velocity, I can find that. I multiply it with my ftx and then update my nu t state. It's a prediction step, correct? Covariance, the same way, but remember, I have to take a differentiation. So here you can see sine becomes cos, cos becomes minus sine, cos becomes minus sine, and then sine becomes cos. Differentiation has happened, and then again it becomes a you multiply it with the fxt equation, and then nicely uh, bundle it all up into this GT matrix to help me update my covariance. Again, because the reason why we are using FX is so that motion only and only impacts robots, not landmarks positions. Right? So we take Jacobian, JXTI, fine, all right. Prediction step, great. Now we need to do updates to this prediction output to do a correction step, right? So to do that, I need my observation. Qt is acting as my observation. Sigma r is standard variation in my range. This is a variation in my bearing, and then stands for the landmark which it is actually. Can not think too much about sigma s because we usually don't use it, so it becomes only two-way, right? Okay, so now in my all my observed features, what does it consist of? It consists of two things. One is my range, the other one is my relative heading, right? So imagine it's like this small drone. The small drone has a range finder, and this small drone is going to estimate, given its own position, it'll estimate how far each obstacle is from it using the range finder, which continuously spins. So from here, you will get to know, okay, what is the range, how far it is, that obstacle from this robot, and at what heading. So if this robot is moving this way, this is the heading at which bearing at which it found that obstacle. So that's what I mean here, right? Great. So I mean, again, so if the landmark was never seen before, we will take the robot's initial observation, I mean, wherever it thinks it is, add that to my relative bearing as well as my relative range, take all that into consideration to find the new actual, I mean, predicted position of my landmark, and then so on and so forth. So here we are also predicting where my landmark is. We do not 100% know where it could be, right? And because I mean we have noisy data on my landmark as well. So that's another thing. Right, so we have measurement noise, this landmark data if the robot has not seen it. If it has, then it just gets on with life. Now what it tries to do is it tries to figure out the Euclidean distance to the landmark from the ego as well as the relative bearing. So fine. Now, till now, what we had been doing was in that fx term which we had before, we were trying to limit the observation states. I mean, the new motion model, the evolution of state due to the motion model, limit that to only my robot states, not my landmarks. Similar thing, we want to try doing here, but little differently, which is that now the observation doesn't really change my model, I mean my robot's position, right? It control position or the control input position or even the evolution of it, it does change my position of the robot. Let me rephrase. Because the new matrix, fxj matrix, is not going to update how my state evolution happens, but it does update through the landmarks what my robot's position is going to be. It will impact those. But the things, when the places where it will impact are will be only for the landmarks which it has detected. So this fxj is that matrix. So it's going to take the 2D maps, the 2D landmark, whatever landmark I detected, right? So let's say 2j I minus 1 and 2j 2n minus 2ij, what it is doing is it's just preventing that particular landmark's x and y location to get masked out. So it's gonna take this, it's gonna take my masked inputs output, take that and use that for my Jacobian, I mean, from when I update my matrix using the Jacobian model, Jacobian of the measurement model. So I do this, I find the new landmark 2n plus 3d in that state, and then I will update it using the Kalman gain which I calculate, and then update that and then using the correction step. All that is good. So now we have a prediction step and a correction step. Now things work out the way we wanted it to. Right. Now, what I wanted to show was this whole thing in working, right? So what you see here is this robot is, because it has detected certain landmarks, is its covariance increasing? No, because motion model update it might be there, but because there is a correction step hitting this robot, it's all stable. The system is stable, right? But once I start going away from this, now what you see is, so I'm not moving the robot. So right now the updation is the state evolution. Because there is no noise in my control, it's just the state evolution expanding it more and more. So that's why it's uniform in nature. But now, as soon as I start moving in a particular direction, right? y- That's how which direction I'm moving, the covariance starts increasing in that. So now uh, disregard this, but now this covariance update which you see, this is now because of my control. So the R of t, it's because of that. Great. So we understood that. Now, when I come close to my landmarks and see, I mean, I'll rerun the simulation again, but you can see that when I initially detect these landmarks, the covariance in that landmark was also very high. But the more I go along with these landmarks, between them, around them, the lesser the covariance will become. But obviously, it will be always be limited to whatever the max, when the lowest covariance we can, considering all the robots, right? And that will definitely uh, play a role in this case as well. So let me rerun it so that it's again observable for all of you. See how the covariance is so high. Now what I'll do is, so this covariance again is because of, because given my robot's initial uh, high covariance, if I detect a landmark, it will also get that same covariance. So let me demonstrate that now. Just go closely with this guy. Yeah. Do you see how big the covariances is? And you saw how big the covariance of the initial position we detected was, right? Now, if I go closer, and now I got the previous covariance of the smaller covariance landmarks into play. As soon as I detected those, the covariance for the landmarks which we observed with high covariance also reduced in number, reduced in the amount. Just a fun fact, so this is basically uh, spelling AIRL in a bit of a low dimensional way, but yeah, all right. So moving forward, I hope I was able to demonstrate the role of the sigma, the role of the covariance increasing as well as how the landmarks play its own role, things like that. Now, a big problem with EKF based approaches is calculation of my Kalman matrix. Why? Because when the covariance matrix which we use, so let me just come back, right? Hey, you see that I'm going to take an inverse using this covariance matrix. That matters because inverse is a heavy operation whenever you do it on a system. And it's even more heavier when your matrix is dense in nature. What I mean by dense here is the cells or the individual points in my matrix are all filled up. And when that happens, so initially it will not happen, right? So like you can see in this picture observation which we have in front of us. At step 0, we had sparsity of 90%. At step 16, the sparsity just becomes zero. Like each element has uh, some sort of a number above that threshold number, whatever we set, and so on and so forth. So 32, 63, and so you can see the evolution of the uh, density with the how many number of steps we do in this bottom right graph. And that's bad because dense matrix operations are difficult and more expensive to do compared to sparse matrix. Now, this is where people started exploring this whole space and they saw that, oh, if you just take an inverse of this covariance matrix, call it information matrix, you get a lot sparser output. And that's that's good. And it's also a lot more predictable compared to my actual covariance matrix. Now, to just demonstrate this, on the left side, this is the environment, the whole run I did. Estimation accuracy, you can check it out, but the main important factor is the sparsity. So I've plotted the matrix, how it looks like using a NumPy feature, plotted that to show how the matrix look in a more a pictographical fashion. And you can see how the sparsity goes from step 0 to step 30. And on the bottom, you have the evolution graph. Interesting thing is the sparsity of the EKF's covariance matrix is around only 13%, whereas EIF, so EIF is extended information filter, its information matrix sparsity is 26.1%. And that's actually good. And we use that and we will use that. So I'll show you how in EIF we'll use this fact to help get better estimation out of our overall system. So till then, I'll see you. Till then, try to go over the particle filter and try to look into how this whole EKF slam worked. Do a walkthrough by yourself is what I would say. Answer this. And yep, till then, I hope we see you guys back for the next lecture.